Okay, so last class we talked about stochastic gradient descent, which is one of the most important algorithms in ML. And as we discussed, it has two significant advantages. One is that the cost per iteration is very slow. So cost per iteration is very low. Okay, and we're trading it off for maybe potentially more rounds compared to gradient descent, but the cost per iteration is very low, and that gives you some meaningful progress even if you're not at the optimum given some time, right? And the other thing I briefly hinted at is that it also has some statistical advantages in the sense that it has some randomness, which can also do better in certain cases. Okay. And after that, we kind of saw how to extend the analysis, the guarantees that we have for gradient descent to stochastic gradient descent as well. And then we started discussing about AdaGrad, which is a method to tune the learning rate based on your current problem. Right? So typically when you're doing gradient descent or stochastic gradient descent, in some sense, these are one parameter algorithms that, we think of them as one parameter algorithms. Usually you kind of, tune it even more, but let's say you're only looking at one parameter, which is the step size. How much of a step do you take in each iteration, right? Initially, you might take bigger steps. Later on, maybe slower, so that you don't overshoot. In AdaGrad, you're trying to adjust this for each different variable. Okay, so you have a large neural network. Maybe some weights are more sensitive. You would like to use a different step size or learning rate for them. Okay, and that's what AdaGrad does. And it does this by kind of this simple formula, which basically accumulates gradients. So if the gradient in one particular direction is oscillating a lot, then over time, its step size is going to decay. Okay, so it's going to be somehow like inversely proportional to the average squared length of the gradient that you see in that particular coordinate. Okay, it's coordinate by coordinate. Okay, all right. So today what we'll do is look at some other extensions of it, which are widely used in practice. We won't be able to go too much into why these things work better compared to, let's say, AdaGrad or so on. So we look at Adam, which is more or less like AdaGrad plus momentum. Momentum is something that we already saw. How do we incorporate it into it? We can, and that's what we'll talk about. And then we'll also talk about something more sophisticated called shampoo. It's a terrible name, but it's okay. We have to live with it. Okay. All right. And I should also say that, maybe, hopefully, we'll see some comparisons between them and then move on to the next subtopic within optimization, which is online learning. Okay. So we'll see what that means and how it connects to optimization again a little later. And as I mentioned in the very beginning, as per the schedule, assignment 1 will be out today at 6 p.m. So everyone who's already registered for the class should already be linked to the corresponding Gradescope assignment and, available on Gradescope. Okay. And yeah, there'll be two versions, one for section 1 and one for section 80. So just please upload to the right section. Right. And it is due 1 week from today, which is April 21. All right. Okay. And I should say, the assignment will have two sort of regular problems and two coding problems. Do not use any generative AI tools. The assignment also says it clearly. As I keep telling you, the point is that many of this is classical, a lot of this is classical material. So obviously the current models can do it. But the point is not for you to use these tools, but I want you to be able to understand how they work and potentially design the next generation. You're not going to be able to do that if you just keep using the same things, right? So just try these things, and there'll be a lot of partial credit for the problems as well. So, just make sure you attend them honestly, and that will go a long way towards kind of helping you with the exam prep as well as understanding the material. Okay. All right. So what is ADAM? Maybe let me first copy AdaGrad. Okay. So so what is this algorithm doing? As I said, somehow you're accumulating or keeping count of how much the gradient is varying along a particular coordinate. Let's say I'm only focusing on the first coordinate. You keep checking, okay, how much has it changed? And there's some sort of average, square root of the whole thing so far, right? And one issue with AdaGrad is that over time, these learning rates might become very small, right? Because every step you're increasing this GI a little bit. And over time, you might just be way too conservative. Okay. And to kind of, maybe get around this, there is a version where you change how you aggregate these gradients. And so what you're doing here is I'm adding up everything in the history so far. So even if I'm in the 1000th iteration, the first iteration has as much importance as 999th iteration, right? But intuitively, what should you do? Any guesses? Like, just think of qualitatively. Exactly, right? So it makes more sense to focus more on the recent steps. Maybe the learning rate initially was something, but that was 1000 steps ago. I should at least have some preference to recency. Okay, but that's not at all present in this equation. Okay, and one simple fix for that is kind of more or less RMS prop or exponentially weighted averages. Okay, so this is a common trick. We've actually seen this implicitly already, but let me write it down explicitly once, and we'll go back to what we did and see how it is similar. Okay, so what is this algorithm? So, okay, that didn't work. We'll make do. Some weird color, but it's okay. Okay. So one thing you can do is instead of doing this average by adding up everything so far, we can give some importance to the recent one, right? So this was a previous one. Instead of this, maybe I'm going to add something like okay. And here, maybe let me use a different color to make it clearer. Okay, think of this as some parameter. Maybe I'm going to set it to be 0.99 or 0.01. So what it's saying is, as time goes on, the previous gradients will keep getting hit with this 1 minus gamma, right? So that means the first one will have much less influence. Effectively, you're only even probably looking at like the last 10 or 20 iterations, okay? And then you can do the same thing. And that's one way to fix it. I think you also need to change this, but let's not, but you take that into account and change this here. All right. Okay, let's, think of that as one additional trick that we can do. Okay. And, actually, it seems like it's usually written this way. It doesn't really matter, but let's stick to, okay, something like this. Right? So this is exponentially weighted averages, meaning with things which are most recent will have a lot more weight in the average compared to the previous one. Okay. All right. So that's the first sort of modification to AeroGrad you can do. And then comes Adam, which is, as I said, in all of this, we are kind of even using the stochastic version already, right? So G is an estimator for the gradient and not necessarily exactly the gradient, right? But we also talked about one more very important idea, which was momentum. And AeroGrad is not using it, SGD is not using it. Can we incorporate momentum into it? Sure, we can. Just add the corresponding equations and let's hope for the best, right? Okay. But let me rewrite the momentum update in a slightly different way. It's exactly the same thing. The heavy ball version, not the Nestros version. Wait, where did it go? So let's talk about adding momentum. So now I want adaptive gradients or adaptive learning rates along with a momentum term. Okay. So we can keep track of this as like the momentum term, right? If we call this, let's say, what should I call it? Yeah, let me call this maybe some MK. Okay. Then you have something that depends on the gradient, and then you have something which depends on momentum, right? So this is why I said, there's some implicit exponential weighted averaging here already. Because if you think of when you expand this equation out, beta is some number which is less than 1. So over time, these momentum terms will keep getting dampened, right? So in some sense, heavy ball was already implicitly using this sort of exponentially weighted averaging, okay? So let's make it more explicit because it makes it easier to write down the final algorithm for Adam, which incorporates both things, okay? So rewriting heavy ball. So I'm going to initialize M0 is 0. And you update momentum term. MK is some beta times MK minus 1 plus GK. Okay. So I'm just going to use a gradient estimator. Once again, we're incorporating momentum with an estimator instead of the actual gradient, right? And then you update the parameters. The final equation is, okay, this is going to be our gradient estimator. And You update the momentum term, and then xk is just xk plus 1 is xk minus eta times nk. Okay, this is just a different way of writing down the same equation. You had alpha and beta as parameters there. Now we have eta and this beta, which are slightly different, but the exact same equation really. Okay. Any questions about this? So this is just a rewriting of the heavy ball. And the point of writing it this way is that now we can think about just changing this eta to incorporate the adaptive. Okay, and that's what will give us, an adaptive version of SGD with momentum. Okay. Any questions? So we are not going to adapt the rate for the momentum. You can potentially think about that, but I don't think you get much savings. You get much more savings when you adapt it here. Right? Yeah. Grad. Yeah. Right. So over time it does. In fact, that's the reason why we are changing it here. Not necessarily. The reason, maybe another way to think about it is we expect to take bigger steps in the beginning. It's not that you're giving it more importance to the first step, but you believe that you're so far away from the optimum that I can be more aggressive in how big a step I take. Yeah, that's because you're taking bigger steps, right? The idea is that as time goes on, maybe you'll converge to somewhere in the middle, and then you want to taper the step size down, okay? And the square root is actually what is suggested by the theory. You can show that this works quite well, okay? And the only place where it doesn't quite work well, is when you're being a bit too conservative, that's all, okay? So you can speed it up in some sense. And we'll see it in action. It's actually as good as the usual gradient descent, but it can do better when there's like wild fluctuations in the step sizes, okay, or the scales of the different parameters. That's what this is addressing, okay? All right. Okay. And so this is just a rewriting of momentum, and now we can put the two together, right? So we're going to change this eta to include adaptive rates, but it makes more sense to do the exponentially weighted average. So that's what ADAM is. It's an optimization procedure, which the paper that introduced this is, at least from a few months ago, the most cited paper in ML. Partly the reason is that it's so simple that you can code it up and then you can run it on any model, okay? The way you derive this algorithm is by thinking about, okay, what happens for convex functions, what happens for smooth functions, and so on. But once you derive the right formulas and update to use, you can just apply it for anything, right? In fact, we're using it in gradient estimators and so on, but that's all fine, okay? So we're going to initialize. So let's say the momentum term is 0, and like there's also a term which corresponds to something like the G's that we were accumulating, okay? And I should say this is ADAM without something called bias correction. It's not the same bias as you were talking about just a moment ago, but it's more to do with, okay, somehow we'll see initially it doesn't take momentum as well into account. So it's a minor fix to do that. But let's not, worry about that. And then for each round, k equals 1 onwards, what do? we're just going to do each one separately, right? So you update the first momentum, right? So you set, uh, let's say GK is gradient estimator. So it's an estimator for gradient f of xk. Okay. And then I compute this guy. It could either be like, some mini batch size sample or anything else that you have. And then we set the momentum term, which is okay. So we are updating the momentum term just as in this equation. So no change there, right? And then you update the GK. So this is like, how did I write it down here? I wrote it down like that. So let me just write it down. Okay, I'm accumulating the squared gradients with this exponential decay factor. Okay. And then the final update is just putting the two together. So xk plus 1 is xk minus some eta divided by square root of okay. Any questions about this? So we had two tricks in the back. We just put the two together, right? So one was using this adaptive things, one was momentum, and that's how you get this.
Professor?
Yeah.
Yeah, is beta 2 the exponentially which term is
Yes, that's the factor which does the exponentially decaying average.
Okay, got you. Thank you.
Okay. And beta 1, as I said, even the momentum heavy ball method that we saw was implicitly already doing exponentially decaying average, right? We just made it more explicit when we wrote it this way so that it's easy to explain. Okay. Yeah. Right. So people have tried that. And so one thing to keep in mind is you could potentially do that. I'm sure people have done that, but presumably this is simple enough. And as I said, when you have stochasticity, right, somehow the advantage of Nestor does shrink. Okay, so when you have the actual gradient estimators, then Nestor is definitely much better. But when you're already working with gradient estimators, right? So somehow that noise is a bigger thing, so you might as well just do this. But people have tried the other version too without, like, I think, significant advantages. Yeah. Oh, yeah. Sorry. No, this is correct, no? Oh, sorry. I think you're right. Thank you. Yeah, this should be MK. Yes, thanks. I thought you were talking about this one, but yeah, this is MK. Yeah. Was that your question too? Yeah. Okay. Perfect. Yeah. Good. Okay. And this is not the exact Adam method. This works reasonably well, but you need to do some small corrections, which are not, I would say, super interesting. They just take into account for something in the beginning. Over time, it just converges to this. So what are the changes that you do? You do a couple of changes. Let me put a hat here. Okay. And what are these hats? Okay, this is some scaling so that, as time goes on, you're doing what you're doing, but initially you want to slightly decrease this magnitude. Okay. And, again, there's a principal way to arrive at these things, but let's not dig deep into it. It's basically in a way to, when you're doing this exponentially weighted average, you want to make it 1 minus beta 1 so that the things add up to 1 in some sense. Okay. All right. And this makes it more robust in the beginning of the training. It's a small difference. Over time, it's exactly the same. Okay. Any questions? So the cool thing here is that, even though we're talking about different things, like, we said stochastic gradient, it solves a different problem. Momentum solves a different problem. Look ahead is solving a different problem. You can put all of these things together in some meaningful ways, right? And that's what we are doing here. Okay. And lastly, so let's take, again, it's helpful to take toy examples. And for that, so one example that we looked at, and we said, if our function was something like this, then AdaGrad makes a lot of sense because I want to have step sizes which should respect the different scales of these two things. The rate at which gradients are changing in x1 will be much slower because of this factor 0.1. Okay, so that's why we said, maybe we should have a bigger step in the first coordinate than in the second coordinate, right? So if you think about how we are scaling the step sizes in AdaGrad and even in Adam, we're never taking correlations into account. We're treating each coordinate as just some kind of separate thing, right? So we're just scaling based on, okay, first coordinate, second coordinate, and things like that. There's some kind of diagonal scaling, right? But, my function could really be something similar, but slightly different. So how do you handle that case? So let's say my function is, what could be similar in spirit, but one where coordinate scaling doesn't make sense. Any guesses? Yeah. Exactly, right? Why should my thing be so axis aligned? Why should I be so lucky in some sense, right? So what if my function is something like, okay. So in this case, really, there is still a direction. Once you rotate it, there is still a direction where the gradients are changing much lower than the other, right? So if I do a basis change, it's exactly the same function, right? But AdaGrad and Adam do not understand that. They don't try to figure out, okay, maybe I should do a basis change here or anything like that. Okay. So if I call this some y1 and this y2, these are still kind of two perpendicular directions. Everything, the geometry, everything should be similar. But if I run AdaGrad or Adam, they will never differentiate between these two directions. In fact, x1 and x2 will behave exactly the same. So all of the step sizes will basically be the same, right? And so for all of these things, so to handle such things, there is a classical optimization procedure called Newton's method. Right? Again, it's too expensive typically in practice. So the right thing to do is to, the right sort of way to scale the gradients is to change the geometry so that it looks the same for every coordinate. That's what we want, right? So when we're doing AdaGrad for this example, we said, implicitly you should scale x2 down or scale x1 up so that the unit is the same in both. Okay. So here it means you should scale y1 and y2, like these directions. Okay, but in for large scale systems, it's difficult to compute the second order information. Okay. But what people use is like a surrogate for that is it's called shampoo. It's some sort of approximate version of what's called Newton's iteration. Okay. So meaning what you do here is, again, I'll write it at a very high level. And once you do this, of course, You can put all of the other tricks back in. You can put momentum here as well, but let me state the version without momentum and to make sense of this new ingredient, okay? So for, you have x0, and then for I equals 1 through, for k equals 0 onwards, you do the same thing. GK is an estimator. For the gradient f of xk. And so this is called preconditioning. Okay, so preconditioning means I'm scaling or rotating my gradient in some way. If you think of Ada, Grad, and Adam, they're really scaling each individual coordinate of your gradient by some number. Whereas now I'm going to allow arbitrary rotations. Okay, so this means I'm going to apply some matrix. Typically, it's written as an inverse, but I don't think the exact form. Is a left-right preconditioners. Okay, so if you have a lot of memory, it's actually memory which is the problem typically, then you can compute the Hessian of the function at xk and then actually do this more exactly, but it's too expensive. So you come up with whatever estimators you have of these two matrices, you just apply. Okay. And then, xk plus 1 is just xk minus eta times this G precondition. Okay. So in some sense, Ada grad is a setting where LK is a diagonal matrix. Yeah. So they are changing this gradient, how we are updating the gradient, right? So think of, let's say, as an example, right now it's more like a meta algorithm. I haven't told you how to compute LK and RK, right? So let's say I want to capture Ada grad here. What can I do? I can set LK inverse to be this diagonal matrix, right? And where this is basically 1 over, or actually, yeah, LK inverse is just going to be 1 over square root GK1 plus epsilon, 1 over square root GK2 plus epsilon, or alpha is calling it, plus 1. Okay, and let's say RK is just identity. Okay, I'm saying, running this is exactly the same as Ada grad. Because when I run, what happens when I run this? In xk plus 1j, I'm doing xkj minus eta divided by the corresponding jth coordinate times the gradient. Okay, so it's some kind of generalization of Ada grad. And it's not specifying how you compute this LK and RK, but typically in Adam and Ada grad, these LK and RK are diagonal matrices. That's what's distinguishing. We are saying you shouldn't really be restricted to diagonal things if you can afford to look at full matrices. The distinct advantage of diagonal things, of course, is that computing this product is very efficient, and you don't even have to store this whole matrix. It's just the diagonal entries, and that's just one vector that you store. Okay, so the memory footprint, the time footprint will be much higher potentially. Okay. You use some other tricks, like what people do is do some kind of block diagonal things and so on. Okay, so instead of just doing diagonal, I might put some small 2 by 2 blocks or 10 by 10 blocks here, right? And that will depend on engineering considerations and how your exact network is. And I'm training a huge network, and maybe I expect these 10 parameters to have a lot of correlations between them. Then I'll put a 10 by 10 block. Okay, full matrix is going to be better in terms of number of rounds, but per cost, the cost per iteration is going to be more expensive. Okay, yeah, yeah. implicitly, that's what we are doing. So you can think of eta grad as estimating the Hessian by just looking at the diagonal entries of the Hessian. We only have access to the gradients, but you do these tricks to kind of get an approximate version. Okay, these are all approximate for general things. Okay, and in some cases, you can even compute some second derivatives. Okay, depending on how much resources you have, there will be a trade-off on what you want to do. Block matrix, sparse matrix, and it also depends on some intuition you have about the network. For example, you might group different layers together, right? So if you have a very deep network with small things, then you might group these parameters into one block. Okay, so you have to play around, right? So eta grad would be bad when you have some correlations like this, right? And you can kind of get some sense of them and use it if there's a trade-off, of course, right? The biggest challenge, I was saying, is memory, right? You cannot store, if the dimension is D, you cannot store D squared parameters typically because D is so huge, right? So you want to compress it somehow. Diagonal is a nice thing to do, but it's not like ideal. Okay. And there are various heuristics to choose these two. Okay, so this is equivalent to eta grad. Okay, so now use various, you can say, heuristics or techniques to update LK command. All right. And of course, you can also throw in the momentum term for good measure. That would just mean I'm adding some momentum thing here. And the final G precondition K, this would become the momentum. All right. Okay, any questions? And so these all make a lot of intuitive sense. As the last one, I think it requires a lot of tuning, and you have to adapt it to the specific network that you have if you want to use it properly. All right, let's see some examples. As I said, let's keep these two examples in mind and see how the different methods run. Obviously, for such a simple method, you don't need any of the fancy tools. But as I keep saying, we do these toy examples to learn what is the right method to use. And of course, you can apply it for even billion parameter networks after that. Okay, so this is just some, this is a heavy ball method, eta grad, Adam without bias correction, adaptive moment estimation. This is with bias correction. And this is shampoo scalable second order optimizer. I said, it's like a conceptual thing. And when you implement it, you have to adapt it properly. Okay. So it's really trying to approximate the inverse of the Hessian by some matrices. Okay, if you know what those are, there's very beautiful theory around it. And that's where this comes from, really. Okay. And okay, so let's see what happens. So here's an example where it's like 0.1 times the first coordinate square times 10 times the second coordinate square. The minimum is at 0, 0. You can compute the gradient, run all of these methods. And Okay, let's go to the plot. Okay, so here you see, Adograd is doing okay, right? But Heavy Ball is doing even better. And Momentum does address some of the issues with changing scales. Adograd is designed for that, but still Heavy Ball is doing better. But of course, Atom, when you put the two together, it's just it's much, much better. Okay. And the right plot really shows kind of the stretched nature of the contour lines, right? So one unit of change in x1 amounts to much less in the objective value than 1 unit of change in the second coordinate, right? So that means that if you think of the contour lines, it's like some stretched, it's a very long ellipse. And starting from here, Adograd is kind of really, this is a downsloping valley that we said, we really don't want to keep oscillating between the two things, go straight down in the ravine. And that's what these methods are doing, which is kind of cool. Okay. All right. And I also have something with Nesterov. And as I said, actually, this is good. So this is the setting where you have the rotated stuff. It's 0.1 times, I think x1 minus x2, but it's a rotated situation with the same example as before, right? So still there is one direction where you should take bigger steps than the other perpendicular direction, but it's not just the axis x1 and x2. And here you can see like Adograd is here. Atom is still doing somewhat better. Heavy Ball is doing better than Adograd. Nesterov beats Atom, but then, as I said, you had to be very careful. It kind of shoots up again and then comes back, right? Whereas Shampoo is just straight down, okay? And of course, it blows up here because, you have to carefully tune the estimators and so on. So one thing to keep in mind is that the sophisticated methods, they can, unless you control for the step sizes and so on, they're not monotone. Gradient descent is reasonably monotone, but the other things you have to really be careful. Okay. And Shampoo is just like, really small error right from the beginning because it adjusts L and R appropriately and figures out the right scale. Once it finds the scale, it's going straight down there. Okay. And you can see the trajectory also. Once it gets here, it's oscillating too much. I think the implementation, you had to put some thresholds on, like where loss function is less than something, then I stop making updates. You have to have some cutoff points. Okay. All right, and here you can see it's again stretched in one direction, and all of the methods are reasonably going along the inside, but Shampoo is just like straight down. Okay. And there are methods in literature like Newton's method, conjugate gradient. All of these are tailored to doing stuff like this. Figure out which direction, kind of should you go the most on. Okay. All right. And then there's also one more crazier function, which is not just an ellipse. And okay. Here, all kinds of stuff happens. You can see the three sort of Atom, RMS prop is the exponentially weighted version of Atom, sorry, of Adograd. I didn't describe it, but I plotted it here. But I wrote down the algorithm, but I didn't call it by its name, which is RMS prop. And yeah, these three are kind of struggling for this particular function. It is still convex, but it's much crazier. Whereas Nesterov is doing very well. Heavy Ball is doing much better. And even Shampoo is only slightly better than these. Okay, yeah. So here, the reason I think they're doing so much better is because when the function changes its directions. As I said, there are many different variations that you can imagine, but only one of them really does the job. Like Nesterov is the only one which gets you this quadratic convergence rate, right? So it's not easy, even though all look similar. Even between heavy ball and Nesterov, you can concoct examples where Nesterov beats heavy ball hands down, right? But there's only one small difference in the update. Okay, but I would say this should not be very concerning because here we're working with exact gradients. When you add noise, I think then somehow these methods will start doing much better. Okay. Yeah, you can see like the trajectories are just like all over the place here. Yeah.
So I wonder like how Newton's method.
Oh, on the quadratic one is just going to converge in like 1 or 2 rounds.
Oh.
Yeah, Newton's method is very good on quadratic ones. Okay. And even for many of these things, I think it would work quite well. But Newton's method, it's not just the time, it's the memory. I think time we are more willing, but if you say somehow instead of requiring like 10 GB of memory, you need 100 GB, which is quadratic blow up. It's just not possible to even run it. Okay. And Newton's method, that's one of the biggest problems, that you have to store the entire matrix, and that's just not possible. And that's why you use these approximations. L and R, like, shampoo is like some kind of trying to approximate Newton's method, really. Okay. And you can really teach a whole class just devoted to all of these methods. There's something called conjugate gradient, which I really, really like. And there's also something called Frank-Wolf algorithm, which is again very different. So all of these different algorithms are there, but we're not going to dig deep into them. Right? So these are the things that are most commonly used for training many ML models. So that's what we're looking at. Any other questions? And I'll share this notebook too. This is much more verbose because I just the original code is very simple, but running the simulations takes you have to choose the parameters properly. Okay, especially when you have things like Nesterov and heavy ball, they're more sensitive. Okay, any more questions? All right, if not, let me stop here with this. Okay. So let me summarize optimization. What did we learn? I would say the main ideas should be that GD is think of it as a meta algorithm. Because it only needs information about the gradient and nothing else. Okay, whatever way you have for computing the gradient, I can run GD on top of it, right? And then we also looked at SGD, which is use estimators for gradient. Okay. Then we had momentum, which is use history of gradients, right? And then we had adaptivity, okay, meaning use, let me say, learn the learning rates to use. Okay. So this step size eta is also called learning rate. So we are, instead of guessing or doing some kind of grid search when you have so many parameters, we're trying to learn what learning rates to use based on the history that we've seen so far. Okay, in fact, that's one way to really derive the theory behind AdaGrad and so on. And then we also had, we briefly entered like preconditioning. Preconditioning means that instead of just scaling each coordinate separately, sometimes you might have to correlate these scales, right? So it's as if you're doing a rotation and then applying diagonal scaling. Okay. And some things that we did not discuss, many things, but first, as I said, there's really beautiful theory around all of these methods. Have been studied for a long time, right? And so one is optimality of first order methods. Or optimality among, maybe. Okay, so why is Nesterov the best possible? If I only give you gradient, exact gradient information, as I said, you cannot do better than this k squared after k rounds, which is pretty amazing that we know what is exactly possible, right? And the other sort of broad conceptual thing which we didn't talk about and is important is back in the first lecture when we motivated gradient descent, we said you're going in the direction of steepest descent, right? So which direction for unit distance gives me the biggest decrease in the function, right? But you can change how you measure distance in steepest descent. Okay, so that's an important idea that we did not cover. This so for this also leads to something called mirror descent. Okay, so in some sense, mirror descent is basically like doing a variable change and then doing gradient descent in the new variable space. So that will be a very different algorithm than doing gradient descent in the original space. Okay, and depending on the problem, there are a lot of sort of ways to figure out what's the right variable change to make. Again, that's the whole theory of mirror descent algorithms, defining potential functions, and so on. And of course, we also did not cover many important heuristics that people use, like gradient clipping. There's something called renormalization, which also can be seen as a heuristic based on gradient descent and so on. Okay, so many things that we did not cover, right? But let me say a few words about how you can extend gradient descent more generally to convex functions. Okay, and as I said, the bedrock for all of these optimization algorithms is the notion of convexity, both in developing the theory and also because it's actually useful in many applications directly, right? So recall we defined the notion of a convex set, right? So we said, a set is convex. C, we define convex function, but you can also define a notion of convex set. C is convex if x1 comma x2 belongs to C, implies that so this is a convex set. Whenever I join any 2 points inside the set, the line segment connecting them is completely inside the set. Okay, that is convex, whereas this is not convex. Right, so if I connect this point here and this point here, the line segment is going outside the set. Okay, and all of the optimization that we did was for unconstrained optimization. Right, we said there's no constraints on where the parameters should lie. What if I tell you the parameters are only allowed to be non-negative? What if I tell you the parameters have to be like a probability distribution? Okay, and you come up with problems like this, right? And so for example, constraint optimization means something like I want to minimize f of x while x is in some convex, some set C. So we saw that if my goal is just to minimize the function f of x, then I can use gradient descent. The way, I can at least apply it and hope that it converges to the mean. But now if I have this additional constraint that my x should be in the convex set, what can I do? Right? It's not clear if there is a natural version because, maybe this is my set. Okay, this is not convex, but this is more or less. So let's say I'm here. This is my x2. I take a gradient step and it takes me here. Okay. But now this is no longer an allowed solution because I have to be in the set C. So what can you do then? Exactly, right? So we're going to again apply something simple, which is, I'll take the gradient step as before. If it's inside the set, I'm happy, all is good. But if it took me outside the set, I'm just going to map it back to the closest point. Okay, so this is going to be x, right? And this is called projected gradient descent. Pick x0, and then for k equals 1 to so on, you first take a gradient update just as before. If it goes out, I'm going to map it back into the set. But which point should I pick in the set? The one that is closest to me. Just a greedy way, I'm going to pick the point which is closest to me in this set. Okay. And then xk plus 1 equals argmin x belongs to C of okay, so move to the closest point in C. Okay. It turns out that as long as you can compute this step, which is basically projection, all the guarantees that we had for gradient descent, stochastic gradient descent, Nestrov's accelerated gradient descent, heavy ball, all of those things apply to projected gradient descent. You don't have to do anything. Every one of those things will work for these constraint optimization problems as long as C is convex. Okay, so not only are we solving unconstrained optimization, you can actually solve constraint optimization just by using this projection. Okay, we're not going to prove it, but it's easy to show. Actually, you just follow the proof of gradient descent and realize that it works even if I just do this projection. You have to just check line by line and things work out. Okay, so let me just state that as a remark for something to keep in mind. Suppose someone tells me, okay, you're only allowed to use non-negative parameters. Maybe it's important for your application that the weights be non-negative because you want some interpretability, let's say. Right? So then I can always do gradient descent, but then project back into the convex. Right? So all guarantees for GD, SGD, NAGD work even for projected variance as long as C is convex. All right. And this, there are also some very important other algorithms in convex optimization that we did not talk about. For example, as I briefly alluded to, linear programming is a convex optimization problem, semi-definite programming. These are all convex optimizations. In fact, linear programming is basically, you can think of it as least squares regression with a non-negativity constraint. So I'm just trying to solve, okay, minimize ax minus b whole squared subject to x being greater than or equal to 0. That's linear programming, right? And I mean, that's one of the most important algorithms outside of optimization. You can use it in many, many different domains. It's widely used, but it just comes down to this. Of course, because of a specialized nature, you wouldn't directly apply projected gradient descent. People have much more sophisticated methods tailored for that specific optimization. Okay. And for example, there's something called ellipsoid algorithm, which involves even weaker guarantees, but we're not going to. All right. Okay, so let me stop with that for regarding optimization, or at least kind of figuring out how GD and etc. work. And then we'll talk about the next topic, which is online learning and how it connects to a different optimization problem, which is again a very important algorithm across many fields. Okay. All right, so let's maybe take a short break of 5 minutes, and then when we come back, 3-4 minutes, and we'll come back and switch to a different topic. Okay, so the next section, which is basically like maybe 2 to 3 lectures, is online learning. Okay, it's you can think of online learning as like a precursor to reinforcement learning, where the problem is less challenging, but you hope to get better guarantees. Okay, all right. And the fundamental sort of constraint or hardship we face in online learning compared to the learning that we saw so far is that we do not get to see the entire data set beforehand. Okay. So like, in the first lecture itself, we said, okay, our setup is, we have this empirical disminimization problem that we are trying to solve. Right? We have this data set, we have the ERM problem, and then we are trying to minimize it. In online learning, the challenge is that we do not get to see. Okay. So meaning it's not like on day one, I give you the entire data set and you make the predictions from then on. On day one, I give you only a little bit of data. You still have to make some prediction, and then I'll give you some more data, some more data, some more data. It's an evolving process. Okay. And can you think of some examples where you're faced with such a situation? Real world examples are, domain specific or applications where you think you deal with such a situation where you see some part of the data and you're already evaluated. You can't wait for everything and then make a prediction. You have to continuously keep making predictions. What are some examples that you might have seen? Stock market is one of the important versions, and that's where many of these algorithms are kind of also independently discovered. What else? Sorry? Recommending system is another. What else? And if you think of gaming, online games, like, let's say poker, for example, right? So you're sitting at a table playing with people, gradually you keep learning this strategy and you keep refining your own strategy, but you can't say, okay, I'm going to just wait for the first 100 games and then start playing, right? You have to continuously keep playing while you're getting more and more data. Yeah, let's say control systems is another. In fact, one of the most important examples is like, autonomous cars, for example. The way they're trained and so on, there's a lot of stuff that happens online. Okay. Okay. So first, before we get there, let's start asking some basic questions. How do I model online learning? Okay, so how to model online learning. So for the traditional setup of learning, we came up with a simple model, and that led us to ERM, and then we stopped. We have a nice optimization problem, input output behavior that we wanted, and we said, okay, let's just focus on that. So let's see if we can get to something like this even in the context of online learning, right? So we want some model, and then it should become like an algorithmic problem that we can try and solve, right? And but just to kind of understand the interaction that we are having. So on day one, you see some example X, right? This is like your X, and then there is a label, right? That you are trying to predict. Okay. So this X could be, for example, in the morning, as soon as stock market opens, you have all of the information from like let's say the political news and what happened the previous days, earnings statements, and so on. And then you have to make a prediction. Okay, is the stock market going to go up or down that day? All right. You make a prediction, you make your bet, and then at the end of the day, after you made the prediction, we see, let me put a hat here, we see the true label. Okay. So every day we have to make the prediction before we see the truth, but after we make the prediction, we get to see the truth. Right? Sometimes you might even see more information, but that's kind of at least the basic setup. And so our strategy is just as before. We have to go from X to a prediction. Okay. And you can say how good is a model? Depends on the loss. Right? The same thing as before. We can say we incur a loss of which is basically y1 hat comma y1. We said the market is going to go up and it went down, so we get a penalty of 1. Right? And then we do the same thing on day 2. We see the input, we have to make a prediction, and then we have the ground truth again. I shouldn't say ground truth, but basically whatever the true label that we see is. And so on and so forth. Okay. So our goal as before is to just kind of, go from X to a prediction Y with the, hope that somehow the total loss that we incur will be small. Right? And we can change the prediction mechanism based on what happened the previous day. Right? So I make some model here. I see some, that is not doing well. So I update the model on day 2. Maybe my fix worked. It did something good. I'll keep it until I see another sort of, bad behavior, and then I recorrect and so on. Okay. All right. So one question is how to compare different models. Okay. So, what are ways to compare different models? Any suggestions, guesses? Yeah. Yeah, so one natural thing is exactly like weighted maybe sum of losses across time. right? So, how much loss you incur one day, second day, third day, the entire thing and so on. Okay. And we'll talk about this. It's a little bit tricky to model it exactly, right? Because unlike before, we really want to make something or have some model which works even when the future is something potentially inconsistent with the past, right? So we'll talk about that maybe after the in the next lecture. But there is a slightly easier but still informative case where you say, okay, there is an actual ground truth. So meaning there is some hypothesis class, and I know that my label is some function from this hypothesis class of the input x, but I don't know what it is. Okay. So over time, we should hope to learn this f star. Okay. This is kind of the easier model. I'm saying, there is a ground truth. Maybe there is a deterministic function that actually predicts exactly the value of whether the stock market is going to go up or not, depending on all of these features. But I don't know what that function is. And over time, I should get closer and closer to that function. Okay. But how do you measure closeness to the function? And we also want to not be like, okay, I'm going to take the first 1,000 days, I'll incur arbitrary losses. From the 1,001th day onwards, okay, I'm going to be very good. In some settings, that's okay. But in many settings, especially where online learning is being used, you don't want to play a model like that, right? You want something which has this sort of, more smooth sort of learning curve, right? Even in the beginning, it's not completely lost. It continuously keeps updating and doing better and better. Right. So one nice goal to hope for, at least in the case of ground truth, and again, as I said, it's like a toy example, but leads us to nice algorithms that we can use when this assumption does not hold even, is what is called the mistake bounded model. Okay, so one question is, okay, how many days till we stop making any mistakes? You want to say, if I'm learning well, after 1,000 days, I've learned everything and I'm going to stop making any mistakes. Okay, that seems like a nice goal, right? But there is a problem here, which is, what if all of my examples are exactly the same? I stopped making mistakes, but I haven't learned what the function is, right? So in some sense, I've solved the problem, but it's not captured by trying to know what f star actually is. Okay? So this leads us to the mistake bounded model, which is the following setup. So there is an underlying true hypothesis class H, and we see we make a prediction, and then there is a true label. Okay. And our goal over time is to minimize the total number of mistakes that we'll make. Maybe you're being silly and giving me the same example X every day. That means I'm not learning what f star is, but I don't need to learn what f star is in that case. I already know the answer, right? So it's saying no matter what sequence you give me, either I learn what the new, if I make a mistake, I learn something from it, or I don't make a mistake at all. Okay, so this is mistake bound, meaning we want an algorithm that will make a fixed and small number of mistakes no matter how long you run, or let's say how long you play. Okay, so no matter how many days you play, I'm only going to make 10 mistakes. That's the guarantee that I want. Kind of very, very strong and pleasing guarantee. So you cannot hope to do this in many situations, but when you can, this is a great guarantee, right? Does it make sense intuitively? At least we're saying no matter how many days we play, maybe you give me completely nonsensical days data because the X's are not very informative, but then that's okay. I'm just not going to make any mistakes. Maybe I don't learn what F star is, but I'm not going to make any mistakes. Okay. All right. So this is, these are called, mistake bounded algorithms. So there is some underlying true hypothesis class, and there's a true function which is giving the true labels. I don't know what that is, but over time, I'm just going to make a finite number of mistakes. Finite also you can quantify, like maybe 10, 100, whatever it is, depending on the dimension, right? And if there's this, the classical learning theory has this notion of pack learning, and it's intimately connected to mistake bounded models and so on. Okay. But let's look at one specific example of a mistake bounded algorithm, which coincidentally is also very historically important. Okay, and this is the algorithm of perceptron, or online learning of half spaces. Okay, so this is same setup. We're doing online learning, but a hypothesis class is just half spaces. So what's a half space? For us, at least, we're just going to look at those going to the origin. So, you have some hyperplane, like a line or something, and all points on one side are going to be labeled positive, and all points on the other side are going to be labeled negative. Okay, it's basically like saying I have some weighted combination of the features, and every time that weighted combination is greater than 0, I'm going to call it a cat. Every time that weighted combination is less than 0, I'm going to call it a dog. Okay, it's a very simple classifier. So we are in some space which is d-dimensional, and f of x is 1 if there is some true W star such that if this is greater than or equal to 0, you say 1, and is minus 1 otherwise. Okay. All right. And what's the online learning problem then? The same thing that we've been talking about. So on day 1, I see some example x1, I make a prediction, and then I see the true label, which is the sign of W star comma x1. I don't know what W star is. I make a prediction, I see this answer. All right, and so on. Day 2, day 3, and so on and so forth. Okay. And the question is there a mistake bounded algorithm? Is there an algorithm that only makes a fixed number and a small number of mistakes? Correct? So this is quite well studied, and we'll use this as an excuse to introduce another important sort of parameter for sort of real value functions. Okay, and this is called the margin. right? So along with the fact that we have a nice hyperplane, which is kind of, sort of a line where all points on one side are positive, all points on the other side are negative. Okay. So one question is, you should imagine intuitively, if there is a gap between the negative and positive, it would be easier to learn, right? If my points are okay, they're negative and positive on either side, but they can come very close to this line, it will be harder for me to learn. Right? Maybe if they only differ in like the 10th decimal and then it becomes negative, it's going to be very brittle, right? So there's this notion of margin that exactly captures that. So let me draw a picture. Okay, we're going to quantify this in a second, but let's assume that not only do we have the separation, but the separation has some buffer error. Okay, meaning the cats and dogs are kind of separated in this high dimensional feature space in a nice way. They're not like very, very close. Okay. So margin is exactly this notion. It's usually denoted gamma, and you have some data points, and the assumption is that none of the data points is very close to the separating plane. Okay, and the right way to quantify margin is to scale things so that it's somewhat scale invariant. You have the slab around this hyperplane, and none of the points are very close to it. Okay. Any questions about the definition? And I should also say that even though half spaces seem very specialized, they are actually used a lot. Maybe not in the original space, but after you do some feature representation or expansion, in the end, you might eventually just run a half space. Okay. So maybe I take a complicated picture, compute some embedding of it or transformation of it or representation using a neural network, but then I might just run a half space classifier on top. Okay. All right. So this is what it looks like. The positives and negatives, they're separated by this gap. Right? And this gap, this notion, this definition is scale invariant. Okay, and even the class is scale invariant. So let us simplify and assume that norm of x2 is 1 for all examples. Again, this is just to reduce notation. Otherwise, you just have to scale things every time, right? And one way to picture margin is saying nothing is very close to this dividing line. So there is always this gap from the separate. Yeah. In fact, SVMs definitely comes from margin. Basically, SVMs are doing margin. They're looking for a large margin classifier. Okay. So, if you haven't heard of SVM, it's some very popular method back in the day. And the way it works is they have what's called soft margin, right? So here we are assuming that, everything which is positive is separated and everything is negative on the opposite side and is separated, right? So there, what you try and do is I'm going to try and find a classifier which, looks as close to this kind of picture as possible. It might misclassify some examples, but I can look at kind of quantifying, okay, maximize the number of things that you classify correctly and with margin. Right? So there's soft margin, like you just bake it into the objective function and you get SVM. Okay. All right. So we have this definition of margin, and so let's say without loss of generality, let's make two simplifying assumptions. Again, these are not strictly needed, but make the notation and everything easier. And also that W star has unit norm. Okay. Why can we make these assumptions? Because we're only looking at whether or not this inner product is positive or negative, right? So if I scale these things, it's not going to change. Okay. All right. And one of the oldest theorems I would say in online learning is this very simple result. And, is that there is an algorithm in the in kind of this online learning setting where the true labels are coming from a half space which has a margin, and that algorithm makes at most 1 over gamma squared plus 1 mistakes. Okay, so you have this margin gamma. You might be working in million dimensions, but as long as my margin is some fixed constant, the number of mistakes I make is at most 1 over gamma squared plus 1. So it doesn't depend on the dimension at all. It only depends on the margin that you have. So if I have a good margin, then I'm going to make a fixed number of mistakes, right? So after that, I'm not going to make any more mistakes. That's the algorithm. Yeah?
This margin is defined on the data.
Yeah, on the data set, or you can think it as like a promise version that, there is some true W star which has a margin.
But like I see the margin here has both W.
Oh, yeah, this should be W star, yeah. Yeah, so basically it's saying there is, as long as there exists one separator which has margin, the guarantee applies. Okay, so you're right. Maybe if I take this line, for example, right, that's also giving me a separator, but it does not have a margin. Now there is no gap, right? But as long as there exists one which is good, we will only make a finite number of mistakes, right? And the good thing here is that we're not making any assumption about the X. They could be in very high dimensions. They could be coming from something very complicated. Like, maybe you take your base, like, pixels, run them through a convolution neural network, and then you have a bunch of features, and then I'm running a linear separator on top of that. In fact, that's how many fine-tuning methods, work. Use transfer learning, where you say, okay, I'm going to use the big network to compute some representation, and then train a small kind of, separator, which works for my specific data set. Okay. So that's why I think, people like half spaces, because you can do other stuff before you apply the half space, which is more complicated. Okay. All right. So how do you prove this thing? And it's a very simple algorithm. And it's also one of the first sort of, maybe uses of stochastic gradient descent implicitly. It's called the perceptron algorithm from 1958 due to Rosenblatt. It's a very simple algorithm, but the history of it is quite complicated. It's very funny. If you ever have the time, I would recommend going up and reading about the history of the algorithm, because I think when it first came about, I believe there was an article in a few years in New York Times or something saying that, okay, we've invented AI. Saying that, okay, we have a system which can solve all problems in machine learning or something like that. So it's very interesting to read how things get blown out. It specifically happened for this particular algorithm. All right. So what is this algorithm? So let's think of what we're going to do, right? So we see an example. So let's say I'm going to draw a two-dimensional picture. Of course, just imagine we're in very high dimensions, and W star is of unit length. X's are also unit length. So each point corresponds to a point on the circle. Again, this is just a caricature for us to understand it. The final thing doesn't depend on the dimension at all, right? So imagine, maybe this is my true hyperplane. Okay. And so meaning this is my W star. We don't know what W star is, right? So everything which has a positive inner product with W star, meaning on this side is positive, everything on the other side is negative, right? But we also have some guarantee that things do not lie very close to this point. Okay, again, we don't know what W star is, but this is the mental picture that we should keep in mind. In some W star, this is what's happening, right? And now, initially you don't know anything. So you start out with, okay, maybe this is my first guess for what W is. I just pick a random point, and this is my W0. Okay. And let's say here's my X1. So my first point is here. It should be a negative point, right? And actually, yeah, this is fine. So now with this vector, it has a positive inner product, right? You can see this angle is less than 90. So W0, our current prediction for X1 would be, okay, it's a cat, it's +1, right? Whereas the true label is -1. So we made a mistake that day. Okay, the first day itself, we made a mistake. So when we make a mistake, we should learn something from it. In particular, we should update our W0, right? So how do you update your W0? So, W0 is some random start vector. And on day I, we see an example. So how do I update it? Any guesses? Suggestions? Intuitively again, so the only thing that we know right now is, or maybe, okay, let's do an easier case first. You have X1 label and our prediction, right? If we don't make a mistake, what do? Keep it the same. That's the easiest decision to make. Don't break what's working, right? So you didn't make a mistake that day, so I'm not going to learn anything. I'm just going to keep it as it is, right? So Wi -1 if no mistake, right? But when we make a mistake, what should I do? So for example, we were doing this, right? So we had the prediction, and this is the true label. Now, intuitively, here what's happening is that we said positive, but the true label was negative. Yeah. But we don't know the correct result. But we don't know W star. We only know the label. We don't know W star, right? But you're on the right track. So the thing is, so the true thing is saying the true label was negative. That means intuitively W0 is pointing in the opposite direction. Yeah, right? So the intuition is X1, if you just do a case analysis, right? The true label was negative, we said positive. That means that somehow X1 is kind of pointing away from the true W star, right? So minus X1 is kind of, along with W star. So I should take a step along that. Okay. So let's do a case analysis. If true label is negative, but prediction is positive, then intuitively we should move in the direction that is opposite to the example. Okay. Oh, I think let me use all superscripts so that I don't. Okay. So whenever I make a mistake and the true label was negative, I should just kind of move in the opposite direction to this example. Again, that will move a little bit towards W star. That's the intuition. Okay. And in the other case, you would do the opposite. If true label is positive, but prediction is negative, meaning you made a mistake, then something like this. Okay. So the second case corresponds to the situation where, maybe it's something, let me have a different vector. Okay, what if this is my x? Okay. So the true label is positive, but I would have said negative. So I should kind of take a step along that direction. So again, it's going to push me a little bit towards W star. That's intuition, right? We're not doing anything complicated. We're just doing something qualitatively meaningful. If if you got the wrong label, you should move in the direction suggested by the true label. Okay. So that's basically it. That's the algorithm, right? And so we have this case analysis, right? If the true label is negative, I'm subtracting. If the true label is positive, I'm adding. So let me just write it down as it is. So it's going to be wi minus 1 plus yi times xi, if a mistake. Okay, so if the label is negative, I'm subtracting. If the label is positive, I'm adding. Right? Fairly intuitive algorithm. And that's it. This algorithm gets you this guarantee, 1 over gamma square plus 1 mistakes. Very simple, intuitive algorithm, and it gets you the guarantee that is best possible, actually. All right? So when we come back in the next lecture, we will see why this theorem is true. The analysis is very simple. And then we'll also see how this connects to what we discussed in the last lectures. All right? Okay, I'll see you all on Wednesday. And remember, homework 1 will be out today. And if you're registered, you should already be added to the grade score for the course. If not, please contact me.